Hello everybody, today I want to solve a problem on Fermat's principle from the Taylor's Classical Mechanics that was suggested by Miguel in the previous video, so thanks a lot to Miguel, and let's dive into the problem. Fermat's principle is often stated as the travel time of a ray of light moving from point A to B is minimum along the actual path. Strictly speaking, it should say that the time is stationary, not minimum. In fact, one can construct situations for which the time is maximum along the actual path. Here's one. Consider the concave hemispherical mirror shown in figure 610, with A and B at opposite ends of a diameter. Consider a ray of light traveling in a vacuum from A to B with one reflection at P, in the same vertical plane as A and B. According to the law of reflection, the actual path goes via point PO at the bottom of the hemisphere. Find the time of travel along the path APB as a function of theta and show that it is maximum at P being equal to PO. Here you can see that I already draw some things on the actual picture that was given in the problem. So here I want to say that we should determine the length of the path. Let's call it L, and it's equal to AP plus PV. We should find both AP and PV. As for AP, we can look at the picture and look at the triangle AOP. It's equilateral, since we're given that this is hemispherical. So to find the length of AP, we should know the angle HOP. The angle AOP is equal to 90 degrees minus theta. Therefore, the angle HOP is equal to 90 degrees minus theta divided by 2, right? And then we can find AP as 2r sine 90 degrees minus theta divided by 2. Alright, and we're doing pretty much the same for PB. We look at the triangle POB, and to determine this angle, POK equal to KOB, obviously, we just realized that POB is equal to 90 degrees plus theta. And that is it. That's the only difference. Then POB is equal to 2r sine 90 degrees plus theta divided by 2. Okay, great. So the formula for L becomes 2r sine 90 degrees plus theta divided by 2 plus sine 90 degrees minus theta divided by 2. I just reversed it, but there's no difference. Okay, so you may think of taking a derivative of this entire thing, right? Whenever you get the signs, you think of this, but you can use a way more simple trigonometry formula, which you can try to determine yourself or search online for it. It's rather simple, and it says that sine A plus sine B is equal to 2 sine A plus B divided by 2 times cosine A minus B divided by 2. Using this, we can find the final formula for L, and it is 2r, let's look at it, 90 degrees plus theta divided by 2 plus 90 degrees minus theta divided by 2 it becomes 90 degrees, and divided by 2 gives us sine of 45 degrees. And as for cosine part, we're getting that 90 minus, so it's minus theta divided by 2, right? And we know that for cosine, it is true that cosine alpha is equal to cosine minus alpha. So the final answer is 2r sine or 45 degrees cosine theta divided by 2, or oh sorry, I forgot to multiply the entire thing by 2. My bad. And so it becomes 4r root of 2 and divided by 2 times cosine theta divided by 2, and it is equal to 2r root of 2 cosine theta divided by 2. And from this, we can find both the time of travel along the path and when it's maximum. Let's first think about its maximum. Looking at the formula, we quickly realize that the length of path will be the biggest when theta is equal to 0, and that is basically what we needed to prove. So L is equal to max when theta is 0. Great. And as for the time of travel along the path, it's just L divided by C, since we were told that this entire thing happens in the vacuum. And so it's 2 times root of 2 r cosine theta divided by 2 divided by C. And that is it. That is a final answer to the problem. Thank you so much for watching. I appreciate your likes and comments very much. And a special thank you to Miguel for suggesting the problem.